All right, here we're going to look at another spherical symmetry situation, but here our sphere is a non-uniform charge density insulated sphere that the charge density as we move further away from the center increases with relationship to that function. If we want to figure out what the electric field is when R is less than capital R, we're going to be within that Gaussian surface, and we're going to call that distance A. Okay. Now, the charge enclosed by that Gaussian surface is not simply a ratio between the total charge and the volume of the sphere and the volume of the Gaussian surface. All right, it's not that simple there. Since if we took a small hollow shell that had a very small thickness dr, okay, and we're able to figure out this small amount of total charge that's contained within there, all right, that amount of charge would be well, the charge density within that little shell would be different than the charge density of a smaller shell, which would also have a small amount of charge on it. So to figure out the total amount of charge enclosed, we would have to add up the amount of dq that's in all of the little different shells as we move further and further away out to the distance that we want. So that the charge enclosed is going to be the sum of all the little dq's of the total volume, which is actually the sum of all the areas of those shells. Times each of their thicknesses up until the total thickness is A. Now we're going to have to use that idea of volume integral as an area of integral with respect to another dimension. If we think about it as here I have a sheet of paper that has side Z, this has side X, and then here has a thickness dy. Now if we stacked a bunch of sheets of paper on top of each other that all have the same thickness dy, eventually we'd end up with a significant thickness. So the area times dy, if we integrate those infinitely small heights from 0 to y, the area of that sheet is going to be x times z. Integrate this with respect to y, you get a volume of xyz. Okay, so the volume is the area, apologize for that, the volume is the area, the integral of the area times its other dimension. Since you probably couldn't see that, let's look at a circular sheet that has height dh. The area of that is pi r squared. So if we wanted to figure out the volume, we'd integrate the area, and if we stacked a bunch of plates on top of each other from 0 to h, we would end up with pi r squared dh. You get pi r squared times h, which is the volume of a cylinder. Okay. So here the amount of charge enclosed is equal to the sum of all the little dq's. All right, so charge enclosed is equal to this. So I'm going to look at this side, okay? And if I move that over, I'm going to have the integral of the function of the density times the area times dr. And that's going to find the total charge enclosed, or, the sum of all the little dq's. So think about it this way. This is charge enclosed. Okay, manipulate it for the charge enclosed, we get that. And we're going to integrate this from the center out to A. So let's plug in our function. And the area of a spherical shell and we get a function with respect to r that we can integrate. So I'm going to take out constants here. 4 pi rho naught over r squared. 0 to a, r squared times r squared is r to the 4th dr. Right? Solving this integral will give us the total amount enclosed at any distance a away while inside of the sphere. All right, so we can integrate r to the 4th. That's going to be 1/5 r to the 5th. Integrated between 0 and a. All the constants still come down, so that the charge enclosed is equal to this, substituting in A. Okay. So now that we have the charge enclosed, that's really the tough part for this problem. Apply Gauss's law. Okay. The area of our Gaussian surface again, that is at distance a away. Substitute in the q enclosed. 4 pi rho naught a to the 5th over 5 r squared epsilon naught. All right, we can see some things canceling here. The 4 pi, 2 of those a's over here. Okay, so that e is equal to rho naught a to the 3rd 5r squared epsilon naught. So these are all constant. The a to the 3rd is the only thing that's not a constant. So if you put this in y equals mx plus b form, this is our slope. Okay, if we were to plot a cubed on the x-axis. I'm going to do a few more videos of examples of varying charge densities so that we can see how to handle different functions. All right, so hopefully that is easy to follow.